Welcome to Chapter 12. We are going to be looking at a new distribution, and we're going to be testing different types of parameters. We're going to be testing things like a distribution. We're going to be testing if two variables are independent. Chapter 12 is going to look at different types of parameters for our inferential statistics. So we have to introduce our new distribution. What we're going to be using in Chapter 12 is a chi-squared distribution. And we use it for a couple different things. We're going to use it to test variance and standard deviation, but not in this class. So what we are going to be doing, like I said, we're going to be testing the independence of two variables, and we're going to see if a frequency distribution fits a specific pattern. And that's what this section is called. It's the chi-square goodness of fit test, or GOF. Okay, now the TI-83s, if you have a TI-83, you actually do not have a calculator function on your calculator, so I'm going to be teaching this section assuming you do not have a calculator function. Okay, so let's hop to it. Let's get to know our chi-squared distribution. Chi is like a fancy X, and then square, we just square it. Like that. So some things that are characteristic of this distribution, it's asymmetrical, so it's not symmetrical. Some other things is, again, we're going to be dependent upon degrees of freedom. So the shape depends on the degree of freedom. And as the degrees of freedom increases, the shape gets more symmetrical. And then finally, what's unique about this compared to your normal curve or your student's t-distribution is all the values of chi-squared are greater than or equal to 0. All right, so let's look at some examples. Let's scroll on down. Here's some examples of your chi-squared. And so we see for low degrees of freedom, so like the 2 and the 5, here's degrees of freedom with 2, right? Very asymmetrical. And then 5 degrees of freedom, still asymmetrical. And as the degrees of freedom increases, we get more and more symmetrical till finally this last one is 30 degrees of freedom. Okay, and then in the back of your formula sheet, in the back of your textbook, there is a table of values for your chi-squared distribution. And the table of values is set up just like a student's t-distribution. So that means on that far left column you have the degrees of freedom, and then the top row is area to the right. Okay, and then you just match everything up and you have your chi-squared value. Okay. Let's see what we're going to be doing with this distribution. And again, it's a goodness of fit test. So we're going to see if variables in a distribution follow a certain distribution. So here we have that a market analyst wished to see whether consumers have any preference among 5 flavors of a new soda. And then we get this following data. Okay. So here's our approach. So if she wants to see if they have any preference, let's assume there is no preference. All right, and under that assumption that there's no preference, let's find the expected values of each category. Again, assuming no preference. All right, and then once we have that information, we can compare it to the actual observations. And we'll call that the observed values. All right, and the observed values come from the sample. And the expected values, we calculate those, all right? So let's look at this. So first we have the same information. We're bringing it back. Here's the observed values is what we got from our sample. Notice it's the same numbers from before. Okay, so the first thing we'd want to do is we'd want to look at the total amount of people in the sample. So we would come here and we would add up 32 plus 28 plus 16 plus 14 plus 10, and there was 100 people in that sample. Okay? So if there was no preference among the 1, 2, 3, 4, 5 categories, how much would be expected to be in each category? It'd be 100 people divided by 5 categories. So that means each expected value would be 20. Okay, so that's how we calculate the expected values. We look at the total, and then essentially this is a uniform distribution. So we had to evenly divide up that 100 into all 5 categories. Okay, so now what we do as far as our approach goes, we're going to compare the expected values to the observed values. So let's write this next part down. So the observed, compared to the expected, I'll say versus expected, they're always going to be different because samples aren't perfect, right? I'll say almost always. But we want to know, is it significantly different enough where we could say, hey, something else is going on. These are not the same distributions. So, but is the difference due to sampling? Like we said before, no samples perfect. All samples have this sampling error. Or is the difference statistically significant? So is there a significant difference between the two? And this isn't an opinion. We would actually have to put it on our chi-square distribution and see if the distribution is significant. Is it considered unusual? Is it considered unusual? Okay, so, and again, it's always nice to kind of hypothesize at this point. 32 and 20 definitely seems like a big difference, but then, 16, 14, what's the cutoff? When will we say, okay, there's definitely a difference, or no, it's probably just due to sampling error? Okay, well, this is a hypothesis test, so let's get on with the show. We're going to state our hypothesis, and this is always the same. The null hypothesis should state that there's no difference or no change. So we'll do this. We'll do it in general, and then we'll do it for our case. So the random variable follows a distribution. That's random variable follows the distribution. And then your alternative, your alternative would say the variable does not follow the distribution. Whew. So random variable does not follow the distribution from the null hypothesis. Okay, so in our example then, let's relate it back to our example. We could say the random variable or the customer preference is uniform, or we can make it relative to the problem. So consumers show no preference. Okay, so essentially a uniform distribution. And then the alternative would be no preference or not uniform. Excuse me, consumers show a preference. And that would mean not uniform. Okay. So here we go. We're going to state, or we're going to select the level of significance. That's normally given to us when we have a problem from our homework on the exam. And remember, alpha, it depends. We choose it beforehand, and it depends on the severity of making a type 1 error, because remember, the probability of a type 1 error is alpha. So if it's a very significant result, making a type 1 error is a very bad thing, we're going to make alpha tiny. Okay, so the expected values, again, they come from H naught. Those are the ones we calculate. So let's see how we're going to do our test statistic. And we have this formula. This formula is going to be given to you on your formula sheet. You also have the assumptions. So when we're running our phantoms, A is the assumptions. You guys are going to check this. All the expected frequencies that we calculate are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. All right, and then our chi-squared, our test statistic is this. It's the sum of observed minus expected squared over the expected. Okay, and then that will follow a chi-squared distribution with k minus 1 degrees of freedom, and k is the amount of categories. So how many categories do we have here? 2, 3, 4, 5. So it's going to be, our degrees of freedom is 5 minus 1, it's 4. Okay, and we're going to have to calculate that. We're going to have to remember that. Okay, so let's go for each category. So notice we have the expected here, and we're going to do observed minus expected. So 32 minus 20, 28 minus 20, 16 minus 20, etc., etc. Let's square it. And then we're going to take that and we're going to divide by the expected. So like 144 divided by 20. 64 divided by 20. 16 divided by 20. Whoops. 36 over 20. 100 over 20. Okay, and then if we add all of that up, that's our formula. And that's our test statistics. So let me change colors. Our notation is chi-squared. Test is statistic, we do the sub-zero. And if you add all those up via calculator, we get 18. Isn't that crazy? Okay, so there's our test statistics. So let's look at our different approaches. Our classical approach, we're going to compare the critical value to the test statistic. Okay, so area, so go reference your chart in the back of the textbook or on your formula sheet. Area to the right is 0.05 because that's the level of significance. And then the degrees of freedom, we said, was 4. So find 0.05 on the top row, 4 on the left column, and if you match it up, our critical value is equal to 9.488. So that's this value right here. And then what about our test statistic 18? Well, that probably be all the way over here, right? Is it in the critical region? Definitely. Okay, so our test statistic is definitely bigger than the critical value. So test statistic is in critical region. So what are we going to do with that null hypothesis? Good, we're going to reject. Reject the null. All right, alternatively, let's look at the p-value approach. So the p-value approach would be the probability we get as extreme or more extreme. And for chi-squared, we do right-tailed test on chi-squared. We do right-tailed tests. So the p-value, it's going to be that chi-squared is greater than or equal to our test statistic, which is 18. So I'll show you on the calculator, but if you want to go to second distribution where you find binomial PDF and CDF and normal CDF, if you search around, you're also going to find chi-squared CDF. And that's how we can calculate area under the chi-squared curve. And the parameters are lower bound, upper bound, and then degrees of freedom. All right, so if we're doing this for this example, seamless, you guys would type in chi-squared CDF, greater than or equal to 18. So we start at 18, go off to infinity, and we have 4 degrees of freedom. And so then we get our p-value after we calculate that, and it's 0.0012. And remember, always with our p-value approach, we compare the p-value to alpha. And how does the p-value compare to alpha? It's much lower. So when the p-value is low, the null must go. So same conclusion, we're still going to reject the null. Okay. So same hypothesis test that we're doing in Chapter 10 and Chapter 11. Even our conclusion is going to be the same. So let's see what our conclusion looks like. So if we reject the null, what kind of evidence do we have? Sufficient evidence. What comes next? At the alpha equals 0.05 level of significance. To conclude, and then always the alternative. And so the alternative was that the consumers show a preference. And it's always nice to kind of take a step back and make sure we understand what we just tested in the results. So did we say that the consumers show a preference or do not show a preference at the end of the day? We said the consumers do show a preference, so that the difference between the uniform and the sample, that difference was significant enough. And so now we're going to say, yes, consumers have a preference, right? And what did they like? They ended up liking definitely cherry the most and grape the least. Grape soda is delicious, so I don't know what their problem is. Okay, let's look at another example. This one's a little bit different because it's not a uniform distribution, so let's see how we're going to handle this situation. So this says, according to the manufacturer of M&Ms, 12% of peanut M&Ms in a bag should be brown, 15% yellow, 12% red, 23% blue, 23% orange, and 15% green. A student wanted to determine whether a randomly selected bag of peanut M&Ms had contents that followed this distribution. He counted the number of M&Ms that were each color and obtained the results shown below. Test the claim that peanut M&Ms follow a distribution stated by M&M at the alpha equals 0.05 level of significance. Okay, so first keyword that should stick out to us is this. This is telling us that it's a hypothesis test, and for hypothesis tests, we follow phantoms. Okay, and the other thing that should stick out, because phantoms P, the parameter, it's a little bit different. It's not a mean or proportion, it's the distribution. All right, so remember these acronyms help organize our thoughts. So for P, we can just write distribution. Next up is H, the hypothesis test. Always the same for a goodness of fit. The null is that the distribution follows the given one. So we could say the M&Ms follow the distribution stated by the manufacturer. And the alternative would be that it doesn't. Okay, good. So next up, phantom. So you have your A is the assumption. And we can't do the assumption yet until we calculate the expected values. So remember, the expected values come from the null hypothesis. So they're going to come from what M&M's has given us. So it's 12%, 15, 12, 23, and 15%. But it has to be percent of the total. So we would first have to figure out how many M&Ms there are. And so we could add up this whole column and see what kind of total we have. And we have 400 M&Ms. So if it did follow the distribution, then the brown should be 12%, 12% of 400. All right, and we would just continue on that pattern. Let's see, 15% are yellow, 12% were brown, 12% are red, 23% are blue. I got confused. And 23% are orange. And then finally 15 are green. I'm having a hard time saying different colors but writing in yellow. It's confusing me. Okay, so we would calculate that out and we get our totals. Okay, so our assumptions are that all the expected frequencies have to be greater than or equal to 1 and no more than 20% or less than 5. Well, we have large numbers, right? Everything is bigger than 5. So we can say all expected frequencies are greater than or equal to 5, and that would satisfy both conditions. So that's what we're going to say. We're going to say all expected frequencies are greater than or equal to 5. Okay. N, name that test. This is your chi-squared goodness of fit test. You can write GOF as well. All right, we want to see if this distribution fits our data. And now T is obtain your test statistic. So remember, we have to look at the difference between the observed values minus the expected values, then square that, divide by the expected, and then add all of those up. So in this case, how many categories do we have? 1, 2, 3, 4, 5, 6. So we would have to do this part 6 times and then add them all up. Okay, so try that out by hand. I'm also going to show you how to use the calculator to make it a little bit easier. So you can look in that in the next video. But in short, you guys can try it on your own by hand. Chi-squared, your test statistic, ends up being 3.5687. Okay, phantoms. O is obtain your p-value. And remember, for the chi-squared test, it's all right-tailed. Go to second distribution, chi-squared CDF. We're starting at our test statistic, going off to infinity. How many degrees of freedom do we have? Good, 6 categories minus 1. So it's 5 degrees of freedom. And if you get that into your calculator, you get this value. Okay, so at this point, we have 2 options. Ooh, I'm running out of room. You could use your classical approach, go into the back with your formula sheet, and find area to the right 0.05 with 5 degrees of freedom. And you'll find on your chart that this is your critical value. And we could see that the test statistic is less. So we're in the okay zone, the do not reject zone. Alternatively, we could look at the p-value approach where we can compare it to alpha, and it's much bigger than alpha. That also tells us we're in the okay zone. So M is do not reject. Make your decision. Okay, and then finally S, state your conclusion. So if we're not rejecting the null, what kind of evidence do we have? There is insufficient evidence at the alpha equals 0.05 level of significance to conclude that, and we always state the alternative, and the alternative is that the M&Ms do not follow the manufacturer's distribution. Okay, lots of writing in these final chapters of our statistics textbook. All right, so what we're going to do now is we are going to go over to our calculator. We're going to see how our calculator can help us through this process, and then we'll do that last example together as well.